Welcome to this session of Shadow the Scientist. My name is Jamika Marshall, and I'm pleased to serve as the Shadow the Scientist Programs Manager. Tonight's topic is exploring the local neighborhood with the Gemini North Telescope. Our science hosts for this session include Charlie Figura and Emily Peavy, Zachary Hartman, and we have Jenny also, who is in the control room. We'll be able to talk to all of them and get an introduction from them as we get into the session. First, I'd like to acknowledge that Shadow the Scientist is an initiative brought to you by an amazing group of people at the University of California at Santa Cruz. Now, as I was saying, in this session, we have the privilege of shadowing members of Gemini Observatory, Gemini North's science team. So we have, we have Jenny and Zach in the control room. Charlie and Emily are in a separate place. And so we'll find out about everything that's going on in just a moment. So a bit of background on the Gemini Observatory here. So the International Gemini Observatory consists of twin 8.1 meter optical infrared telescopes that are located on two of the best observing sites on the planet. Now, Gemini North is located on Hawaii's Mauna Kea and is part of an international community of observatories. By incorporating technologies such as the laser guide star adaptive optics and multi-object spectroscopy, astronomers in the Gemini partnership explore the universe in truly unprecedented detail. Now, tonight's observations are taking place in the control room of the Hilo Base Facility, and that is where we can find Charlie, Emily, Zach, and Jenny. Now, we have a brand new science host tonight. That's Charlie Figura. So let's go over to Charlie now to get us started. Charlie, welcome and thank you for being our science host tonight.
It's good to be here, Jamika. Aloha kako. Hello, everybody. My name is Charlie Figuera. I am one of the science operations staff here at the observatory. I'm also a research astronomer, although my research is typically done with other telescopes. Um, my job here at the observatory is to do a lot of what's being done in the control room right now, both to operate the telescope and to observe with the telescope, plus a few other tasks that the science operations staff helps out with. And we're going to try to take you through what we're doing tonight and give you a little view of what's happening. What the life of the night crew at the telescope here looks like. We've got Emily Peavy over here next to me.
Aloha, everybody.
Here you go.
Here, I'll switch off yours. Aloha, everybody. My name is Emily Peavy. I am the Senior Education and Engagement Assistant here at the Gemini North Telescope. So my job is to think about all the amazing science and work that is done here at the observatory and think about the best ways in order to be communicating that to people like you and also be taking it to a bunch of our schools on island. As Jamika mentioned, the Gemini North Observatory, well, Gemini North Telescope, is situated on the mountain of Mauna Kea in Hawaii, and then our base facility is in Hilo, Hawaii. So we're also thinking about the best ways that we can use our observatory and our science to connect to our community here in Hawaii, and that's a lot of what I do.
Thank you, Emily. Thank you, Charlie. And we have things going on in the control room. Now, I believe Jenny muted the microphone there because they are actually taking care of some business there because observing is already underway, right, Charlie?
That is correct. We start observing at basically at nautical twilight, which is a point at which the sun is about 12 degrees, the end of nautical twilight, when the sun is about 12 degrees below the horizon. What that means for your personal experiences, it still may be light enough in the sky to see silhouettes, but you're not going to make out any detail of, even if somebody's standing near you. So that's about the time when it's dark enough that we can actually start doing the scientific work. And that happened about, I believe that happened about 18, 20 minutes ago. So they've gotten underway. Um, they are working on, I think, their first observation tonight. We have, weather conditions at the observatory. Let me share a couple of things with you. Probably the first thing I would like to share with you is, here, we, as Jamaica mentioned, we have one of the best astronomical sites in the world here on Maunakea, but we do have a very special set of environmental conditions that we have to work with. So
We are sitting on and near active volcanoes.
we are. So about 30 miles south of us is the summit of Kilauea, the youngest and most active volcano in the Hawaiian Islands and on the island of Hawaii. And you can see here an image of Halema'uma'u, the crater within the summit caldera of Kilauea. We have had some very lovely eruptions going all day. In the past 20, 30 minutes, we had a very high fountaining around 700 to 1,000 feet, I would estimate. And it has just sort of stopped. And you can see the bright area there on the screen where one of the two, there's basically two vents right next to each other there. And that is where we had lava fountaining from. And you can actually see the flow up from that lava down into the right of that image.
And raise your hands if you guys have been hearing about Kilauea erupting on the news lately, because it has been getting shared on the news a lot.
Yeah.
Yeah, it's really interesting because I'm here in Anchorage in Alaska at the summer meeting for the American Astronomical Society, and one of the volcanoes here is at yellow alert. And
that's right.
yes, and so just 2 days ago, when I was on a tour, they were talking about how this was dominating the news cycle, and I thought, wow, I hadn't seen anything about the volcano here erupting, but only been seeing news about Kilauea. So
Right.
it's really interesting.
And Alaska volcanoes are a lot spookier because you guys are stratovolcanoes. We're shield volcanoes. When we erupt, everything stays in its same location. We're safe. I actually live only about like less than 15 miles away from it. And I'm like, hey, yeah, it's erupting, it's happening. But what does an erupting volcano mean for us at the observatory?
All right. So
Exactly.
So the volcano presents two major threats to us that we need to worry about. So let's be clear, this is Kilauea. It is south, a little bit east, but mostly south of Maunakea, which is the shield volcano that the observatories are located on. Both Maunakea and Kilauea are classified as active. However, Kilauea is the only one that has erupted in the past few years. I guess Mauna Loa erupted about 2 years ago. So the two primary threats that Kilauea presents to us are particulate matter. So the volcanic ash that gets sent aloft. There basically, when you're thinking about volcanic ash, you don't want to think about about like ash from a campfire. This is actually little tiny bits of rock. This is lava that is spattered off, usually during that fountaining, into just little tiny bits, and it solidifies, and it kind of looks like a wet ash when it lands, but it is rock. And so in that, if we get very high fountaining, for example, the particulate can get up into the, get up above our inversion layer. It can get above 10,000, 11,000 feet, and then it can get carried over and potentially deposited onto, well, it'll get deposited onto anything, but we'd rather not get deposited onto our mirror, because that, getting rock on your mirror is usually not good for your mirror. So that is one thing that one of the two primary threats. The other primary threat are the volcanic gases. And if you look at that camera right now, you look at that screen, you can see all of this outgassing. That gas is primarily composed of water vapor, believe it or not, but also things like sulfur dioxide. And that sulfur dioxide can be a very caustic, or is a very caustic gas. It can cause breathing problems if you breathe it in, and it will have corrosive effects on things like mirror coatings. So we watch out for both of those things up at the summit. Now, under nominal conditions, our prevailing winds here, blowing from east to west, will often carry those gases, what we call VOG, volcanic fog, out to the west of the island. But it is not unusual for winds to carry that back up around the west side of Mauna Loa and come back up toward Maunakea that way. And of course, if we get really high fountaining like we saw today, that not necessarily will, but can put that ash high up enough that it can get carried over to us as well. So that can be a threat. We monitor things like that. Let me show you. So this is actually a particle detector from the Canada, France, Hawaii telescope, which is located immediately to the north of our facility. And you can see basically this plot is showing particle counts over the past few days, I think we got the past week shown here on the bottom, the past day shown on the top. And what you can see is we did see some high counts indicated by the vertical spikes. If we look at that upper part, we can see those high counts shown by a few of those dots there. But for the most part, our particle levels have stayed pretty low. So all the fountaining that we saw today doesn't seem to have presented much of a threat to us tonight. And so the night crew took a look at this, and they decided it's safe to open, and they can get underway. They'll keep an eye on detectors like this to determine if a threat develops, because we can have a case where, as you saw, the fountaining had slowed down. We didn't, it was looking like everything was coming to a stop for this particular episode. The particle, the VOG and the volcanic ash are still there. They're still up in the atmosphere. Obviously, as you saw, Kilauea is still outgassing that VOG, so it can still present a threat even though the fountaining is over. So they'll keep an eye on that all throughout the night tonight. And if those levels start to spike, they will have to close the telescope to prevent any kind of damage, possible damage to the telescope.
So this active monitoring of all the things going on, but especially this activity down at Kilauea, is being done in real time here in the control room. Now, we have two amazing astronomers there with us. Zachary Hartman, who is a postdoctoral fellow at NASA Ames Research Center. And then we also have one of the amazing Gemini staff there, Jenny, who we can see with Zach back there waving. Hi. I don't know if we're able to chat with them just right now. I see Zach's on the phone and troubleshooting.
Yeah, why don't we
Can
pause for a little bit? Let's not disturb them just yet until they get their, I think they've got some issues they're working on.
Okay, so there are two positions here in the control room. Tell us about Jenny's role, and hopefully she'll be able to chat with us in a little bit.
Great. So Jenny is acting as operator tonight. The science operations staff, what we call the SOS, Science Operations Support, the SOS team can serve in either of our two night crew roles. Ginny is acting as operator tonight. So that means that she is in charge of the health and safety of the telescope first and foremost. And she's also in charge of conducting all of the telescope motions. So she is watching over the telescope itself, the instruments, the facilities to make sure that everything is working the way that it should and to keep it working if a problem shows up. And problems do show up. This telescope is coming up on 25 years old. It saw first light in, actually it is, we are at 25 years old. We're
Wow.
25.
Yeah.
We are over 25 years old. The first light was in 1999. I don't know the month or date.
Oh, June. I don't know the date
So
exactly.
we are really right on
Our
25.
telescope is old enough to rent a car.
But so she is going, there's a lot of components and things do go wrong. She is the person who is going to address any issues that come up, keep the telescope safe. And she's also the one who is going to look at the weather conditions, including looking at the at particle counts like this. She'll also look at cloud conditions, look for signs of precipitation, and she'll be the one that says, we're closing up, that we cannot guarantee the safety of the telescope if we stay open. But that's basically her role as operator.
Now,
Uh, yeah.
that role has, I mean, there's so much responsibility in Jenny's role. So what if you're in the science observing mode and everything seems to be going well, right? And so I imagine Zach now is in the astronomer seat. And
Right.
when it comes between the two, when the final call has to be made about closing or stopping, who has that final say in the control room of the two of them?
It's all the operator. Now there's an interesting dynamic here because the observer, the astronomer, is in some sense in control of the night. They're going to be looking at all of the observations that we do. They're going to be conducting those observations. They're going to be choosing which observations we do. We run a queue system, which is a little bit different from what a lot of other telescopes do. We can talk about that here in a little bit, but as the observer, Zach is going to be in control of where we are going. So he will choose, we're going to go look at this target and we're going to execute these observations. He's in a very real sense, he's in charge of what we're doing over the course of the night, but the operator can override the observer in the regard of safety to the facility and safety to the equipment. So when it comes down to it, the observer could be sitting there saying, wait, we've only got 3 minutes left. Can't we wait? And the operator says, no, we got to close now. Now, generally, the operator and observer are working together and they are checking with each other. I mean, often, there'll be times where we'll be in there and it'll look like we are seeing some potentially dangerous conditions coming up, some high humidity. We've got 1 minute left on this. Yeah, we can do that. I think we're okay to sit. We're safe to sit here for a bit. We'll finish this observation and then we close right away. So it's not a territorial issue. We really work with each other to try to get the best, to get the most good data that we can, but we do not put the telescope at risk.
Brilliant, brilliant. So we have our first question in the chat, and it is from Rick. Rick asks, if needed, how long does it take to close the dome?
Great question. So the dome has essentially 3 doors that open up. The big one, the primary one is what we call the shutter. That's the actual slit that the telescope is looking through. The shutter takes a little while to close. It's about a good, if it's fully open, it's going to take 8 to 10 minutes to close completely. It is a great big amount of metal and it moves slowly because it is that big. It's, it's one of those things when I first started, when I started working here, I was amazed at how slow the shutter moved. When I first got to go up to the site and go in and see the shutter move, I thought, oh, well, no, it actually moves surprisingly fast for its size. It's immense. The other openings to the dome are called the vent gates. These are openings on the side that allow fresh air to circulate through the dome. And that helps us avoid poor seeing conditions that we sometimes get as a result of stale air trapped in the dome itself. The vent gates close very quickly. Even when they are fully open, they will close in the span of 20 seconds. They will close to a stop. So for the shutter, it will take a little bit to close. So then we want to act as conservatively as we can. If we are seeing evidence of precipitation, so sometimes we'll look at a cloud layer and we'll see little tendrils coming down from the cloud layer overhead. This is called virga, and it's basically indications of precipitation. We start seeing signs of virga, we're closing up as fast as we possibly can.
So for perspective, like how big are like these vent gates and like the shutter? Like as tall as a person or
Oh, much greater.
Okay.
Much greater. I can't tell you a dimension off the top of my head. The vent gates, well, so the main mirror of the telescope is 8.1 meters or about 27 feet. And I did this because I always, I used to teach astronomy and I always like to put things into terms that people can understand. That's about 1.75 Toyota Tacomas long across. So, that's our main mirror. And the shutter is a bit wider than that. So we're looking at 30, estimate 35 feet across. And then it runs the entire height of the dome. So it's a substantially large hunk of metal. It's not a single piece of metal, it's pieces, but it's a spectacularly large amount of metal that's moving there.
Now, right now, Jenny and Zach are troubleshooting some things happening. So we're going to come back to them in just a little bit, but we can actually see what's going on at the summit live right now, various ways, but I've dropped one link in the chat. I love this link. It's the National Astronomical Observatory of Japan, Subaru's cameras. They have 2 views of the summit. So the first one that I put in is looking from the western side of the summit facing east. And so Charlie, could you maybe click on that and share your screen, or I can do it and share screen? What do you prefer?
I've got it right here.
Amazing. Let's orient everybody first. And I was hoping we'd have a better view of the vent gates, but
Yeah. Fortunately, we're kind of backlit with the moonlight
Yeah.
to the southeast right now.
yeah,
Who am I? It's me. I just pulled up a picture for some reference. Okay.
oh,
There you go.
go for it, Emily. Let's do you first, and then we'll have the live view from Charlie.
Okay.
Oh, I thought I was sharing.
Okay.
Why am I not? Oh, I see what happened. You got it.
Alright.
Yep, you're good.
All right. So, okay. So, this is a picture of a lot of what Charlie was talking about inside the dome. So you can see these are the vent gates that Charlie was talking about. And I was, like, even in my head, I'm like, going, like, is it as big as a person sort of thing? But no, this is much bigger. This is I would probably estimate eyeballing like at least 20 feet.
Oh, substantial. You can see John White standing over there on the floor. So I'm going to go with like 40 feet.
I didn't even see those guys.
Yeah, so you can see you can see a couple of people down there.
Every time I go up to the summit and I'm inside this telescope, I forget how big it is until I walk into the room. But yeah, so here you can see some of our day crew at the bottom here. Here's the vent gates. As Charlie mentioned, the purpose of the vent gates is in order to help airflow move through the telescope, and that actually improves the seeing of the telescope. And then this is the slit that the telescope is observing out of. And here you get a really great perspective of the mirror. The mirror is 8 meters in diameter. So Gemini Observatory is in the larger class of single piece mirror telescopes. If there's an engineering limit around how big you can build a single piece mirror, and that turns out to be around 8 meters. And my joke, the story that I always like to tell though, is just over 25 years ago when Gemini was working on construction and then working on first light, Gemini was thinking that, oh yeah, we're going to be the biggest single piece mirror observatory that you can possibly get. And then not long after that, Subaru, so we're 8.2 meters. And then not long after that, Subaru came online, and Subaru is 8.3 meters. So they're our neighbors, we love them, but they did steal that title away from us of the largest single piece mirror.
And Emily, isn't the HET telescope even bigger?
Which one?
HET, but is it segmented? Hobby Eboli?
My understanding is larger than 8 meters, you need to be segmented. I know Keck is segmented. I'm not sure about HET.
I'll check it out. Hobby
Okay.
Eboli. I'll look it up.
So I'd like to welcome here. This is a new voice. This is the founder of Shadow the Scientist, Raja Guhathakurtha, who's joining us from Los Altos in California. Yes, so Raja, let us know. You can drop it in the chat so we can have a better idea of these sizes and who's just a bit larger than Gemini. And so for everyone, this image, I put a link to this image in the chat in case you'd like to grab it. It is beautiful. And of course, looking out through those vent gates, you get to see that sunset there through the vent gates, that nice pink color, and you can see a little bit of the clouds beneath the telescope. And yes, Roger says it is segmented. So yes, Emily, absolutely right. Absolutely right. Well done. So now that we're oriented with the telescope and the vent gate, Charlie, can you show us what's happening right now on the summit?
Working on an emergency in the control room, but I can show you guys.
Oh, Charlie is okay. Gotcha.
Yeah. So, but I can be here with you guys for a little
Please,
bit.
please do, Emily. So yeah, so this is the link that I dropped in the chat. Now, this is the view from the western side of the summit looking east. And so, Emily, first tell us what are these two big domes here on the left, and maybe you can go around the edge and tell us where we can find Gemini out of all these.
So, yes, Gemini Observatory is one of 11 international observatories at the summit of Maunakea. About half of them are optical infrared like Gemini, and about half of them are submillimeter or radio telescopes. So that makes a difference in how you set up your telescope. So in this image, the two that are in our foreground, these are the Keck twins, operated by the W.M. Keck Observatory, but two telescopes. These are 10-meter observatories. And as I was mentioning before, to get larger than 8 meters, you do need a segmented mirror. So that means that instead of having one single piece, the mirror is a bunch of little pieces that can be removed and then put back in. The advantage of that is if you're needing to do any maintenance on the mirror, you can just be removing a segment and then replacing it with a similar segment, so the mirror doesn't come off completely offline for an extended period of time. Gemini, when it's time for us to do maintenance on our mirror, we are off the sky for a long time.
Which one, do you know which one is which? Which Keck is which?
I want to say foreground is 1 and then background is 2.
Correct.
There you go, 1 and 2.
1 and 2.
Yeah.
Nice.
And then sitting behind that, there is the NASA IRTF, which is an infrared telescope. And our operator, Jenny, also works both at Gemini and at IRTF. And then this is the Canada, France, Hawaii telescope. And then this one right here is us with Gemini. And then just behind that is the UH 2.2 meter telescope. And right now I'm like looking at these beautiful stars coming in the background, and I'm seeing what I can recognize in the stars in the background. The thing about Mauna Kea is summit of Mauna Kea, it is so beautiful and clear there that even if you have a really good sense of the nighttime sky, you see so many more stars than you would from the ground level. And so sometimes even recognizable constellations will get a little bit lost. Yeah.
Thank you so much. Thank you, Emily. And so Charlie, you're back.
I'm back.
You were dealing with some emergency in the control room. What's going on?
Right. All right. So what's going on? They're troubleshooting one of our essentially our newest instrument called IGRINS 2. It's having a little bit of problem. It's trying to communicate with our control system. In particular, it's trying to give offsets, which basically means directions to the telescope on how to shift very slightly where it's pointing. We're looking at very, very small adjustments to make sure that the target is centered. And those offsets, it's sending those offsets, but the offsets are not being received. So there is something wrong with the communication between the instrument, between IGRINS and the telescope. And so I was trying to help them troubleshoot. They're going to see if they can talk to, unfortunately, I was not able to give them much guidance on this particular fault. I have seen a lot of different failure modes for a lot of different instruments, and I am on the IGRINS team, but this is not a failure mode that I have seen yet before. So they're going to try to put in a call and see if they can solve that. Now, one of the things that makes Gemini not unique, but definitely in a minority, is the fact that we have multiple instruments on the telescope at any given time. Many telescopes are single instrument telescopes for the course of the night. They might have multiple instruments, but to change instruments, it takes significant physical labor and time. So that might be something that the day crew does during the day. Now, when we talk about instruments, you want to be thinking about the thing that's actually recording the scientific data, the camera, essentially. So you might imagine that different instruments allow you to do different things. They might allow you to look in different parts of the electromagnetic spectrum. We have one of our instruments that is very good for visible and near infrared light. We have other instruments that specialize in the near infrared. We even have an instrument that goes up to the mid-infrared. That one has not been in use for a little while. But we have all of these instruments, some of which do imaging, some of which do spectroscopy. So instead of making a pretty picture, that you might expect to see. They're going to split the light up into the components, so we can learn things about what's giving off the light. We can learn things about composition. We can learn things about motion, about their dynamics, how they're moving in space relative to us.
And if I can just add, and then you can
Yeah,
jump back in.
please.
So earlier we took a look at the telescope and we were able to see that mirror. And so how our telescope is working is that our primary mirror, 8.2 meter primary mirror, is the light collector. Once light is collected onto with that mirror, it is then reflected to the secondary mirror, which then helps focus the light. And then you might have noticed that with our primary mirror, there was a hole in the center, and then that's on the other end of the secondary mirror. And the secondary mirror will then send that light through the primary mirror to what you're looking at here. And this is what is sitting on the back side of the telescope. This is the ISS, which stands for Instrument Support System. And even though it's on the back side of the telescope, it is the ISS, not the ASS. That's my new favorite joke, lady. Anyway,
That's good. I like that.
so what's one thing that makes Gemini really, really special? So I mentioned earlier that larger telescopes these days tend to be segmented mirrors, and an advantage to being a segmented mirror is that you can be removing pieces of the mirror if you're ever needing to do maintenance on the mirror, and that's an advantage that that type of telescope has. But every single observatory ends up getting some different advantages or disadvantages. And one advantage that Gemini has over some of our neighbor observatories is that all of our instruments are, well, not all of them, but I believe up to 5 instruments
Up to 5.
are all located on this instrument support system that is all situated on the backside of the telescope. We can't see all 5 of here easily, but we have one here, 2 on the other end, and then another one we can have connected to an optical cable that will actually go down underneath the floor here and into the structure of the telescope itself. That's very useful for some of our instruments that need to be kept at very, very cold temperatures. Now, one of the biggest advantages to this is we are operating with Q observing. So there's a plan for the night, and our operators, our scientists are working to go through that plan. But say something new happens in the sky and we get an alert that says, like, hey, stop what you're doing right now and go check out this gravitational wave detection somewhere in the sky. Well, our operators are able, if they need to switch instruments, they can just tell a mirror in the very center of the structure to switch to a different instrument and go to a different area of the sky, and they can be adjusting to new plans on it. Yeah, our instrument support structure really helps us here.
There's pros and cons. A lot of the facilities that have single instrument, those instruments may individually they might be larger and have in some ways better capabilities than we have, but the ability to be switch and go from one to another to another. We will have some programs that we conduct where one PI, one principal investigator, one scientist has a set of observations. They're going to look at this particular object, and first they're going to do visible light imaging, and then they're going to do visible light spectroscopy, and then they're going to do infrared spectroscopy, and they're going to do a different infrared spectroscopy in a slightly different wavelength range, and they may switch between 3 different instruments for one set of observations, and we can do that all for them in one night in one small block of time. It takes somewhere between 1 to 2 minutes to switch instruments out for us, and that mostly is because the tertiary mirror, what we call the science fold, the little mirror that Emily mentioned that sits down in the bottom to direct the light, it's very, very high precision, and it just takes a long while for it to move to the correct position. And that's really all of the instrument change time that we have. That's very different from a place like CFHT right next door to us, where they have instrument change day. And so it's, they have a day in a week where they're going to switch and they're going to go to this instrument, and they can only do observations with that instrument until they change. And it seems to be more the norm for a lot of places to have a single instrument on the telescope at a time. We are not unique in this, but we are definitely in the minority. But it's a very nice capability for us to have.
So, Emily, Charlie, you can mount up to 4, 5 instruments at once at any given time on the telescope. When does this happen? And who does this? Tell us about the day crew.
So the day crew is a group of technicians and engineers um, who work at the summit generally 4 to 5 days out of the week. I think they're generally on 4-day shifts. Um, they go up, basically they go up to the summit fairly early in the morning, not in the wee hours, but definitely before a lot of people have had their coffee yet. Um, they will stop at Halepahaku at the 9,000 foot level and have breakfast there at the astronomers residence up there, just a little bit mouth of the visitor center. They'll and during that time that they're having breakfast at the cafeteria there, their bodies will be acclimating. We try to acclimate for at least 30 minutes before we go up to the summit, because going from sea level to 14,000 feet is hard on the body. Frankly, being at 14,000 feet is high on the body. And if we were, I think it's about 40 feet higher in elevation, we would be required to wear oxygen at all times. As it is, we have oxygen available up there, but it's there if you feel like you need it. And you probably will feel like you need it. High elevation makes you lightheaded. It will give you headaches. The summit is very, very dry, so mucous membranes will dry out. Your nose, your lips, your skin will dry out fairly quickly. Some of the most important things you can do up at the summit are go slow, drink lots of water, keep applying lip balm. So the summit crew, we have a team, a very, very talented team of engineers and technicians who keep the telescope working. They will do repairs, they will install new equipment, they'll replace things. They're there every day to make sure that we can observe at night. I would not be able to do my job in the control room. Ginny and Zach would not be able to do their jobs in the control room without this crew, and they are amazing. One of the things I like to do during some of my daytime operations is go up there and work with them, learning a bit about what they do and assisting them with what they do up there. And I am never anything but incredibly impressed, because they are working in this very difficult environment.
Yeah.
I once made the mistake, the first time I think I was up there, I made the mistake of trying to run up the stairwell from the summit control room up to the observing floor, basically 4 flights of stairs. I had to go lay down in the control room and get oxygen pretty much right away. I was sick just from that kind of exertion. And I did not even make it all the way up. It's hard on the body. We also get what you call we joke about getting altitude stupid. There's less oxygen in the air. And so your thinking will tend to get a little bit slower, a little bit fuzzier. So it's a difficult environment up there, and they're up there working all day long. Generally, they try to come down, they're generally back down to Hilo somewhere around 6 o'clock, maybe in the evening. So they have a very, very long day. And a long day, even a short day at elevation feels like a long day. So they are doing long days at elevation.
And they're doing hard work when they're up there
Oh, yeah.
too, and it's so impressive to me. It's also one thing I will say is it's very common misconception that to be working at an observatory, you need to have a PhD in astronomy. But a lot of our most essential staff are these engineers and technicians that are working at the summit. And some of our technicians went to community college and worked in the trades and got built up a lot of skill sets. And then we're able to use those skills in order to keep these incredibly complex instruments and observatories operational, and we are always eternally grateful for them.
So their own training may be, as Emily mentioned, from a variety of different sources. They are mechanical engineers, they are electrical engineers, optical engineers. They're also welders and plumbers and electricians. So we have a we just have a very broad array of talents that are required to keep a place like this working. It is amazingly complex. When the operator is monitoring systems over the course of the night, we're largely only monitoring a small subset of the total number of systems. We have warnings and alerts that will tell us if something goes wrong in something else, but there is just a phenomenally large number of components that make this telescope work.
So I see we
All
have
right. So
a really deep question in the chat that we might want to think about first.
yeah, I wanted to get to that question in the chat, but first I want to make sure that I thank everyone on the day crew, because as you said, if without them, evening observations would not happen. So
Would
thank
not, absolutely. They
Thank you.
are, I have nothing but the greatest respect for them. They are spectacular and they do an incredible job.
Amazing. Thank you. Okay, so Emily, would you like to read this question we have in the
So this is a deep, thoughtful one sort of thing. And Charlie, as much as I think it's addressed to you, but if you want us to jump back on our perspective, because I think this is definitely I think so many people coming from science backgrounds will have slightly different perspectives on this. But the question reads, Dear Charlie Figura, in the book You Are the Placebo by Dr. Joy Dispenza, it talks about how belief can affect changes in the body. Do you think something similar happens in astronomy, where what scientists expect or believe might change how they understand space data, like when looking for dark matter or signs of alien life?
So to me, this is a very easy answer. And the answer is absolutely. Everything that we do as scientists happens in context. It happened, when we as scientists try to interpret new data, it's not tabula rasa. It's not a blank slate. We are always interpreting data in light of information that we already have. If you think that there's aliens and that they're everywhere, you're going to start finding signs of aliens everywhere. Fortunately, while that's true, science has a very important way to safeguard itself. And I think it's one of the things that makes science unique from all of the other ways that we have of understanding. There's a lot of different ways we have of understanding the world. We can understand things, certain aspects of things better through art, through poetry, through music, through meditation. But science does something that those do not. Because what we do as scientists is we look at data, we look at an idea, and I think what surprises people is that the very first thing we try to do when we think we have an idea is we try to prove it wrong. If I get a signal and I think this is a weird signal, I'd wonder if this is aliens. And in fact, that's kind of that's actually a true thing that that has happened on multiple occasions. But in particular, I am thinking of the in 1967,
I'm not going to get any.
1967,
Stars, right?
I'm thinking pulsars. The astronomer got got a weird signal that repeated on a very clock-like cadence. And no one had ever seen anything like this before. The only time you ever see anything that repeats so regularly, to our experience, was something mechanical, something Earth-made. Thank you, Raja. Jocelyn Bell. We're going to give Jocelyn Bell the credit.
Yes.
I am not going to give Anthony Hewitt the credit because he did not do the work. He took the credit for her work. He did not do the work.
So
And I will get very uppity about that one. But Jocelyn Bell discovered this, and she made a note on the chart recorder because, her radio telescope wasn't recording digital data at the time. It was like a chart recorder, like you might see like a seismograph. And she wrote the letters LGM. You might know what the LGM stands for here? Emily knows.
Little green men.
Little green men. LGM ? Not necessarily that that's what she thought it was, but that's sort of where the mind goes. This is a signal nothing like any natural thing that we have ever seen before, but it looks like man-made things. It looks like human-made things. So you start to get an idea and you may be serious about that idea or you may not be. Jocelyn Bell was not very serious about that idea, but I think it was tongue-in-cheek humor more than anything else. But what you do then as the astronomer is you try to find ways to break your idea. All right, is there anything else that could make something like this? If it was caused by intelligence, what would happen? How could we test that? And as they continued to collect data and sort of fill out the large picture, it became apparent that these things were associated with areas where there were exploded stars, what we call supernova remnants. These are the end of very high mass stars 8 times the mass of our sun and larger. When they explode, it's a tremendous explosion that would destroy anything around it. And these signals were coming from there. That doesn't sound like anything that you could construct could survive that. So maybe it's not little green men. But I think that's sort of that, to get back to your original question, yeah, obviously everything we learn, we observe, we automatically try to fit that in the context of what we already know. And the most exciting thing we do is when we find something that we cannot make fit. And it breaks what we know. And I think a lot of people think that scientists want to prove their ideas right. And really, we get excited about proving ideas wrong.
Yeah.
Because when you prove something wrong, that opens up the doorway to actually learn new things and come up with some things that nobody has ever seen before. I'm sorry, that was a long-winded explanation.
No, that's
Guys,
it's a very deep question.
Just to
and
let you know that we're done troubleshooting at the control room. So if you guys want to ask us any questions or
Absolutely.
Yes. Okay, let me stop my share here. of what's going on the summit. And yeah, let's pop over to Jenny and Zach. Charlie, thank you for that in-depth answer. That was great. Yes, 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 you're welcome. Wonderful. Okay, Jenny, Zach, what's the status of things now? You're done with the troubleshooting, and congratulations on that. Where do things stand, Jenny?
What was the question you asked? Sorry.
Where do things stand? How is Igrins?
Oh, okay. Igrins was not communicating. Yes, we rebooted TCS and that solved the problem. So we only had to call like 3 people.
Oh, very good. I wish I'd thought to suggest that. You tried restarting the Igrins OBS app, but not TCC. Okay.
So
So, oh,
what's
yeah.
that acronym? TCS, TCC? What is this?
TCS is a telescope control system. So that is essentially the system of computers that is directly responsible for coordinating movements of the telescope. So when the observer um, or when the observer asks the operator to move to a new target, the operator will load that program in and issue a slew command, a movement command, and it is the TCS that is actually going to be interpreting that command and basically sending out commands to the individual components of the telescope. So it's going to send one command or one set of commands to the mount base to rotate. It's going to send another set of commands to the mount base to tilt. It's going to send a set of commands to the secondary mirror, to the mirror support system. It's going to basically send lots of different commands, and because these are all things that you could conceivably do individually, the TCS does all of that. So it's in some ways sort of the brain of the telescope. Everything tends to go through the TCS when we are operating at night.
And now I get to fill out a fault report so that everybody can follow up on it tomorrow morning and make sure that it was what we thought it was, and that if it happens again, we can easily search it for a fix.
Right. So this is a big part, of having this complex equipment. And as I've mentioned, some of the components are old, some of them are new. Igrins is a year old, basically. And we're very excited because this year is the first time that we've offered it for science observation. It was on the telescope last year, but it was for testing purposes only. We don't want to put an instrument on the telescope if we can't guarantee the validity of the scientific data that it's going to collect. So we do go through a lot of testing to make sure everything's operating correctly, to make sure that the scientific data we're getting is meaningful, that it's giving us what we think it's giving us. But so that's a very new system. And so there's going to be a lot of places where it may not play as well with our older systems as we would like it to. So as Jenny mentioned, one of the things that she needs to do as operator is to file fault reports to say, here's what happened, here are the circumstances when it happened, here's the time when it happened. And then the next day, the engineers, the technicians can go and look at instrument logs. They can go and look at all of this recorded data, not the scientific data, but all of the statuses, the output of all of these individual systems, and find out what broke and why. And hopefully, if all goes well, they'll be able to look and say, oh, this fault happened because too many signals were coming in and TCS stopped listening, because TCS got confused and went into a panic state. They'll be able to figure out what it is and hopefully fix it so that doesn't happen again. At the very least, we'll put it in a list of problems that we know can happen. So I mentioned, when I first came back from the control room, I said, this is a failure mode that I hadn't seen with this instrument before. Now we're going to have an entry in our reference guide that will be able to say, hey, I had this problem with iGrins. Oh, this is how you fix a problem when it's not talking to TCS anymore. And then that means that instead of spending 30 minutes trying to figure out what the heck is going on and calling 3 different people, the operator can just fix it.
That's
Yes,
amazing.
documentation is really annoying, but it's my favorite thing when we are when it's nighttime and we're in a big rush to fix stuff.
Yeah. It's amazing. It's I always point out that, when I first started doing this, I was calling out frequently. A problem would occur, I couldn't figure out how to fix it. I would call out and, to one of our point of contact engineers to say, hey, can you help me fix this? And over time, as I learn how to use that reference material, I call out very, very rarely now because we have this big repository of things. We know there's so many things that we know can go wrong, and we know how to fix them. So we try to keep that amount of time that we're not actually operating, we're not taking data, try to keep that as small as possible. And nobody wants to wake up and engineer at 2 in the morning anyway.
At least not if you can help it.
No, I never want to. I will.
Well, is it weird for me to say there are facilities where people do prefer to be called in the middle of the night instead of referring to documentation because it's job security?
That is true. I won't argue. I won't argue if they like to get called. I always feel bad calling somebody. I don't want to wake somebody up if I can help it.
The job security is a very important thing these days.
Very true.
These
Very.
days, no kidding.
Mm-hmm. So now that you fix the fault with iGrins, you restarted the telescope control system. Is iGrins is now working properly? So is this? I know you have Q observing mode, and iGrins' main goal, I believe, is to look at young stars to understand this kind of the early stages of development. Is that, do I have the right understanding?
Wait, we missed out on one of the observations. Unfortunately, we had to move to another. But Zach, do you want to talk about what you're looking at?
Yeah, so I mean, so that is one of the potential the potential science cases for iGrins. There are a couple of others as well. Actually, what we're looking at right now is potential stars that are candidate planet hosts, and we're trying to characterize them by looking at their spectra and seeing the abundances there. So that's what the program that we're looking at right now is, and we're taking data, so that's great. But there's the characterizing the young stars. These are actually some of the ultra cool dwarfs. So they are. I haven't looked at the abstract, but I'm assuming they are low mass stars, much with masses much lower than our own sun. And so they're trying to figure out their properties and seeing, if they do in the hope that eventually they may yield to be, or they may be found to be planet hosts. So that is my understanding of what we are trying to look at through this program. iGrins 2 is also really great for looking at exoplanet atmospheres. And also binary stars. So it is a wide range of science cases that it can be used for. And there are a lot of programs here at Gemini that are looking at each one.
I'm going to jump in just a moment here. I'm going to share a view of what the IGRINS data looks like. So this, what you see on the screen here, is the last data that was collected by IGRINS. It's currently conducting a new exposure, collecting more data, but this is the last set of data that it wrote out. IGRINS is a really interesting instrument. It's an infrared spectrometer, and it's covering two different bands of the infrared spectrum from, I think, about 1.9 micron to about 2.1 or 2.2 micron wavelengths. So a micron is a millionth of a meter. So this is much longer wavelength than visible light, infrared, near infrared. But it covers all of that simultaneously. So if you look at the data display here, there are, there are two boxes sort of in the middle, and those are these two bands, what we call the H band and the K band. And what we're looking at, if I can zoom in here, oh, not that far. The spectrum is a series of these bright lines that we're looking at. So each one of these lines corresponds to an element or a molecule that is giving off light. And so we're collecting that light from that distant star. We're splitting it up and looking at all of these different colors. So what we can do are all these different, I'm going to be careful here. We're looking at all these different wavelengths, all these different lines here, these spectral lines that you see as these vertical bright lines, and even some fainter lines there. We interpret those wavelengths essentially as color. They are color in the same way that red, blue, and green are color. They're just colors we can't see with our own eyes. And those can tell us about composition. They can tell us about dynamics. We can learn how things are moving. We can learn things about temperature in some, in some cases. So there's a lot that we can actually learn from looking at spectroscopy. The bottom image is what we call the slit viewing camera. So this is actually showing us, in order to, for the light to get into the spectrometer, it has to pass through a narrow slit. And we actually have a camera on IGRINS that looks at that slit to make sure that the star, the source that we're trying to collect data for, is lined up on that slit. And you can see our star sitting right there at the bottom edge of that, at the bottom end of that slit. And over the course of the observation, the telescope will jog back and forth and put the star at one end of the slit and put the star at the other end of the slit, so that we can do some complicated analysis to help handle with noise reduction and to get a better overall signal. But that's what the data that we're looking at looks like. The colors that you see here, the blue, greens, and yellows, are not in themselves meaningful. It's a color map that helps us distinguish between the bright and dark regions on the data. So the blues and greens and yellows, that's not the color that I'm talking about. That's just so we can see the data, because this is infrared. We can't see infrared light, so we don't have any meaningful ways to ascribe color to it in any, in the way that we would for visible light data. IGRINS is actually really good at looking at a whole host of different things. I know IGRINS is very good at studying, because it's a very high resolution spectrometer, can distinguish very, very fine differences in color. It's very good at looking at binary star systems. It's very good at looking at cases where you have a star and some companion. But there's a whole host of different possibilities, different science tasks that you could use.
This is it's brilliant to be able to see this data here, and the description that you gave us, so that we understand what we're seeing is really wonderful. Thank you, Charlie, and Zach and Jenny. Um, if I could just pivot quickly to a question we have in the chat, and then can come back to the science we have, that you were talking to us about, Charlie. Emily, would you like to read this question from Blue Moon?
Sure. Yeah. So, how do you conceptualize the role of your own intuition as scientists when stuck with some hypothesis or some data? I think we have some deep questions that are really thinking about humans being scientists and then the nature of humans and our faults of humans, as we're also thinking about hard logic.
Absolutely. Absolutely. So I think, in that intuition is critical, because intuition is essentially that tool that's allowing you to find places in the framework of our knowledge to fit this new piece in. We see this weird thing come out. Jocelyn Bell saw this weird data spike, this thing that gave off this signal on these very regular intervals, every like second and a half or so. Tick, 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 tick. Well, what could cause that? And then you start to think about all the things that you know, and that's really there's your intuition. You start to think about all the things that you can imagine. Well, a clock can do that. Well, why does a clock do that? Well, a clock might do that because there's an armature that's turning and an escarpment that's restricting the motion. And so you have this tick, tick, tick of a mechanical clock. And so then your intuition might say rotation. If something was rotating, that might start to get this regular signal. So essentially your intuition is that tool that's going to allow you to use all this other stuff that you know, the stuff that you've learned in school, the stuff that you've learned through your experience, and just try to figure out ways that this new piece of information might fit in. So I really think, I think that's that role. And I think that, that's a place where I think, for all the machine learning that we can do, that's a that's the thing that humans do exceptionally well. And we also can fall into traps, obviously, that way, where our intuition can lead us astray and we are just way off base. But that's where that other aspect we were talking about before comes in. You test for failure. You try to break your idea. So even if I go way off on the wrong direction, because my next step is to try to prove myself wrong, hopefully I will be good at that part. Do you have a
Yeah, I have some thoughts, and this is more leading to the question before, but I think both of the questions that we got so far are very much thinking about the role of us being humans and having human error and within science, when science wants to be something that is very, very logical and very straight. And I think a lot of what Charlie was saying is very, very, it's all it's science working perfectly means that scientists are questioning their own science and wanting to prove themselves wrong. And I think more often than not, science is working that way. But just as we have great examples of people wanting to be proving themselves wrong, I think we also have many, many examples throughout scientific history of people allowing their egos to get in the way and
yeah,
wanting to be right because they feel like they should be right. And I think that's also the two examples that come to my mind. Oh, I forgot my second one, but one that often comes to my mind with that is there was a scientist, and I actually forget his name, who in the 1800s, a lot of people across science thought that space should not be vacuum. There should be this substance in space that was referred to as the ether. And there was a scientist that came up with an experiment in order to be observing the ether, and it never worked. And he spent his entire career refining this instrument in order to find this ether. And he he wasted his entire career trying to find it, but never expanded to the idea that he might be wrong, that maybe it's not actually there.
But it made for some really good fictional stories and
Oh,
books.
yeah, it does.
That would be, you are thinking of Michelson
Thank you. Yes, I could not think of his
and the Michelson-Morley experiment.
you.
Oh, Michelson Morley, yes, awesome.
And the second example that I thought was also Lord Kelvin. I can't remember his name. And he was smart with doing a bunch of other stuff, but one thing, Lord Kelvin was convinced that by his calculations the sun should only be a few thousand years old, and he refused to listen to evidence of geologists, and he was very insistent, and he was wrong. Would never have lived long enough in order to realize why he was wrong,
Right.
but he would not set aside his ego to think that he might be wrong. And so, but thinking of this perspective though is also like the examples that I am pushing out in here is also two examples of very specific demographics of people who have really dominated sciences. And I think when we are able to allow diversity and allow other perspectives into science, we are also working on ways to be breaking down some of this biases that can come from people and their egos.
Right. I'm a little more forgiving of Kelvin in this regard, but only a little bit. I mean, but that's a great example because Kelvin could not conceive of how you would get the energy to fuel a star other than by gravitational contraction. It's easy to show that the sun is not on fire because combustion would last, if the sun was combusting, it would have enough fuel to run, I don't remember what the number is, 1,000 years maybe, tops. And we have recorded history, I mean, good recorded history longer than that. So we know that's not right. And he came up with a solution that got pushed out to around, if I recall correctly, around 8 to 10,000 years. And Kelvin I mean, there's two issues here. One is Kelvin, there was no other energy source that he knew of and that anybody knew of. It wasn't until the early 20th century that we discovered what fusion was. Kelvin was talking about before we even knew what subatomic particles were. So he had no way of understanding the energy source. But he also fell into another trap because 8 to 10,000 years is kind of the ballpark that is consistent with certain religious beliefs about the start of the world. And that tickled his own personal biases. And so he, it's easy to understand how he got narrowed into that particular viewpoint. So on one hand, I'm kind of want to give him a little bit of grace because there's no way he could have known. On the other hand, he did allow his biases because there's nothing wrong with saying we don't have anything. The ideal thing that I would like to have seen Calvin do in that case, that I'd like to see a scientist do now, is to say, you know what, I don't know. And it's okay not to know.
Oh, yeah.
And I think that's one of the things that it's really hard. It's hard for us today to say, you know what, don't know. We just don't know.
I wish people would say, I don't know, when they didn't know more often, because
Right?
that is so annoying when people let their ego speak for them and they don't just admit that they don't know.
It never ends well.
It leads you down really terrible paths.
I'll say if you guys ever want to read some really, really amusing like science history, Kelvin got into some vicious fights with geologists of his time and Charles Darwin, because Charles Darwin was friends with geologists, and geologists were picking up rocks going, this rock is a few million years old. How can this rock be older than the sun? And there is letters of him talking back and forth with Darwin and other geologists that they're like spitting venom at each other.
Like I said, I could give Kelvin a little bit of grace, but not a lot, because Kelvin definitely he had blinders on, he had his view. And I mean, we don't have to pick on somebody from the 1800s that way. I mean, that is a problem we run into. And I think, as good scientists, when science works well, we're trying to disprove our theories, we're trying to disprove our hypotheses, and we're trying to find ways that the science breaks. We're trying to prove ourselves wrong. But it
These
doesn't always work that way.
these responses are so great. I love that each of you have shared a perspective. Yes. Emily, there's a question. What's the name of that book that
Oh
you're
man, I'm like,
referring to?
I'm looking to find some resources because I know the letters exist. I forget where I saw them, so I'm going to see if I can find a resource that'll send back to them, and I'll put that comment in the chat.
Okay, brilliant. Thank you so much. And so thank you for these responses to the questions are just really intuitive and so human. And I am grateful that you all feel comfortable sharing that. Now back to what's on the screen, and those of
Yeah.
you in the chat, keep those great questions coming, drop them in the chat, and we'll definitely get to to any questions that you have for us. So now, Zach, Jenny, Charlie, Emily, things on the screen have changed. They're all different. What's going on? What's happening? And that's for anyone to jump in and bring us up to date.
Zach, you want to give us a little discussion of what we're seeing?
Yeah, sure. So for each of these Argus 2, for each of these targets that we're looking at with Argus 2, we take a standard star to kind of give us an idea of
We're guiding at 50 hertz.
to kind of give us an idea uh, of what a spectra should look like for a typical star, and also to map out how the Earth's atmosphere is affecting the spectra. And so we take these standards of these really bright stars. You can see on the screen that is a very, very, very bright star in the lower left image. You can actually see that there's saturation in the middle, as evidenced by it appears to be a circle in the middle. At least I think on that one, yeah, you can kind of see it. And also it's red if you really glance at it. Which is great.
I can zoom in a little bit here.
Since those colors are describing brightness, that's why it's red, is because that's the side of the spectrum that would be the brightest for the what is it, like an over mapping or overlay? What would you call it?
So yeah, so actually the standard data color map here runs from sort of a dark blue to the bright yellow. The red is a separate mask that we apply to that the view data display program here applies to pixels whose value is off scale. So it's high off the chart. So it just maps those as red to make sure that the observer knows we've got saturation here. We're collecting too much light for that particular detector to handle. If we see that kind of red, those saturated pixels in the data up on the upper two images, we would have to do something about that. For the slit viewing camera here, we're not too worried. The slit viewing camera is not being used for scientific purposes. It's doing, we have that to make sure that everything is aligned on the slit correctly. So if it's a little saturated, and for a star like this, a standard star is standard stars are typically very bright. It's going to tend to be saturated, and that's okay. Yeah, so as Zach mentioned, we need, when we're collecting data, we need we need a reference, we need a comparison. Each of these very faint lines here corresponds to a particular wavelength, but we don't necessarily know what wavelength it is. So when we look at a standard star, we know what the wavelengths are for each of these lines for that standard star. So then now we can take that and we can compare that to the data from the unknown and use it to calibrate the scale, basically to figure out where the 0 is on the ruler to make everything else line up correctly.
We're in an SVC image right now, so it's gonna change.
Okay. The other thing, as Zach mentioned, the other thing that happens is in the infrared, there we go. So Zach is taking an SVC image, a slit viewer camera image, and that's to make sure that things are lined up correctly to start with. So that's, we saw that the star was centered on the slit. Everything was correct. We move off the slit. We're going to end up moving back onto it, move the star back onto it, and then start collecting data. And then again, we're going to see that, as it shifts back and forth from one end of the slit to the other. As we've been talking and data has been rolling in, you may have seen that star on the previous data sets move from the bottom right corner to the upper right corner of that slit as the telescope is jogging back and forth, doing these offsets. And again, those offsets are there to help us get the best possible data, to get the least possible noise so we can see faint signals more clearly, basically.
So while we're here with a new image here that we were just talking about, could we segue over to a few questions for a moment and then come back to Zach and Jenny with the amazing science data we have going here. Emily, would you like to, well, first, thank you for putting a link to the discussions about the letters. I think you have something in from JSTOR there. So thank you for that, Emily. And then now we have a few questions. Maybe we can take one and then pop back over to the science because Charlie was showing us something really interesting right there, and I want to dig into that.
Talking.
Oh,
or sorry, he's working on something.
I was trying to. I wanted to show something and I have lost the window that I was looking at.
Well, we'll let you find that while we this question. This question is for anyone. Jenny, Zach, Emily, Charlie. First question. Yes, please, Emily, go ahead.
I was going to jump to the question I'm a bit more equipped to answer, so I might jump around the questions and not.
Go for it.
So I was going to, let's start with from your experience so far, what would you regard as the most complex or puzzling thing you've worked on? And I'm going to answer this one a bit personally, and I think this is going to get into some of the nature of what our discussion is. So me personally, when I started thinking about astronomy, when I decided to go to school in order to be an astronomer, I always joke that my very first astro class, I sat down and I realized I was a very weird astronomer, that even though I loved astronomy so much, I also liked talking with people, and most astronomers don't. And so my career ended up going into the path of education, engagement, and communication of astronomy. But getting into the most complex or puzzly thing that I've worked on is, I'll say, humans are really complex beings. And so navigating perspectives and thinking about communication while navigating perspectives, and thinking about living in a very, very changing world with unique perspectives on the world and on science becomes very challenging. And I won't shy away from the thought that also astronomy existing in Hawaii and on a place that is considered to be very, very sacred, and having to think about the best ways that we can be engaging with our community, acknowledging mistakes that might have been made in the past, and also finding our best ways forward is a very complex topic. And sometimes as much as I fought for my C's in my physics classes, sometimes I miss a little bit more of the hard labor of that.
Fair. Fair, yeah. I definitely think, it's funny because I can think of a lot of things in astronomy that are very complex. Some things that some of the things I've worked on, some things that colleagues of mine have worked on. Anything involving fluids is insanely hard. And fluids are important in space. You don't think about it, but the whole behavior of a star is all, I mean, it's a lot of fluid motion as you have this high density gas, which behaves kind of like a fluid moving around. So, I mean, that's very complicated stuff. And any calculations done with that are very, very intensive. But, you start to talk about the interaction of people and astronomy or people in science in general. It's like, oh yeah, no, fluid dynamics is fine. I can do that.
I love
Everyone
it.
has their own battles.
Everyone has their own battles. Yeah.
This is so true. So true. Um, Jenny or Zach, would you like to add anything for that question?
I kind of want to comment on what was already answered. The whole
Please.
not talking to people thing. I love it. Like I love just sitting in a basement by myself, staring at the wall in the dark and not having to deal with anyone. But I learned that if you want to get funding, you you have to go out into the world and convince everyone to give you money. So that means you have to be a little bit of a people person, even if you don't want to be, for astronomy. And then also regarding the fluid dynamics, that one's fun because I've tried before to try to use fluid dynamics to calculate, sort of to analyze paddling, because we paddle out here in Hawaii, 6-man canoe races. And I was trying to use what I had learned in mathematics and physics to analyze our paddling techniques. And as soon I could do it with some periodic, analysis like sinusoidal waves and stuff like that. But as soon as I got into the fluid dynamics, it was like every complex thing I added, like, oh, you have to consider this. Oh, and if you consider that, you have to consider this. Oh, and if you consider that, you have to consider this. It got so complex that I just felt like I was drowning in an endless sea of you can never get close to the answer because the closer you get, the further away you are because you realize how much more you're missing in your calculations. So I could relate to what both of you guys were saying. That's that's going to be my take on that question.
Drowning is not helpful when you're paddling.
No.
It's so true.
Well, I did make some pretty fascinating presentations that convinced a bunch of new paddlers that timing is the most important part of paddling.
I would definitely, I don't paddle, but I would definitely think so.
Yeah, it has to do with canceling out other people's efforts. If you all do the same thing in the same way at the same time, you can sort of resonate your power and make yourself, faster. But then bring in fluid dynamics, and the faster you go, the more resistance you're getting from the water. So, yay!
So I was going to give you this little view. This is one of the many, many windows that we monitor over the course of the night. And this is what we call our TSD, our telescope status display. And this is basically showing us what the telescope is doing right this moment. So we can see we're pointed at this object. We've got a location in right ascension and declination, or altitude, elevation and azimuth. We can see from the errors here. Errors here means not mistake, but rather deviation from expected. That our errors are very, very small, which means the telescope is pointing where it should be to within a fraction of an arc second. So that's really, really good. We can see sort of a schematic view of what the telescope, where the telescope is pointing. You can see we've got vent gates that are open a little bit. It looks like they're probably open about 10, maybe 10% right there. So the slit is fully open. And we are tracking an object that is, we're looking toward the southwest, so that object track will be this way. So as we continue to observe, that object will be decreasing in elevation. This is our 30-degree line. So it's 30 degrees off the horizon, and it will be setting as it gets closer this way. But we can also see about, that the moon is off to the to the southeast here, and we have a wind indicator as well. Probably one of the most interesting things on this is the little diagram over toward the right. You can see these white rays, these white lines, and and a bunch of green boxes and things. So this is sort of a little schematic view of the telescope. The large green lines represent the primary mirror. So light comes in from the top. Those are our vertical lines coming in from the top, and is reflected to the secondary, which is that green rectangle. And from there, light is reflected down toward the ISS, the instrument support stage. And so we see our science fold, the tertiary mirror that's going to direct light to the different instruments. Here we see 4 instruments indicated around the science fold. Light is currently going toward instrument 3, which is labeled as IGRNS 2. So that's the IGRNS data that we were just looking at. We do have 5 instrument ports on the telescope. The other one, number 1, is the bottom port, and that's where we have a different instrument called Maroon X currently located. But so the operating crew can look at that and see exactly what the telescope is doing. The fact that all these lines are green means that everything is behaving the way it should. If they turn red, there's a problem. Something's wrong. There's a fault somewhere. And
Or they're not being used, they're not engaged.
Or they're not engaged. So if you look over to the right, you'll see a bunch of things that are red. Those are basically off. They're not in use. So that's okay. If things on that telescope diagram are red, that's not good. That's not just a matter of not in use. That's a not good. Something's wrong. But you can see all of the information that is being represented here about where the light is traveling, where all of these different components are pointing. We have cable wraps, because when you've got rotating parts of the telescope and you need to get cables up to them, you need to have a way for the cable to not get twisted. So there are some complex systems that allow us to rotate the telescope without twisting cables, so that's represented there as azimuth wrap and rotator wrap. All of these different things, all of this data, most of this data is going through the TCS, the telescope control system that we talked about before. So it is monitoring all of these different channels of information, and one of the things it's doing is it's able to present it to us in this way that we can look at and see all of these systems at once. So I wanted to show you a little bit. This is one of the tools that the night crew here is using to keep an eye on what's going on in the telescope right now.
Thank you for orienting us on this, Charlie, because this is really dynamic, and there's so much great information here, so that we can really have a fuller view and sense of what's happening. And now, everything that's happening with the telescope, all the movements, everything, that's all Jenny, right? Jenny is responsible for all of these things. So when we see the light shift from one mirror to another or any of that, that's all Jenny.
So sometimes we'll see light shift. That's basically the scientific observations are set up basically like a computer program. There's a set of instructions in each observation that say, we're going to point here, we're going to collect this data, we're going to shift a little bit, we're going to collect some more data. You know, that when we looked at Igrans, we saw that the star kept shifting along that slit. The program was essentially, that program said, we're going to start here, we're going to offset, and we're going to offset back, and we're going to keep going back and forth. So there's some motions that are being controlled not directly by Jenny, but by the observing program. So Zach is going to start that program, and then that program is going to run, and essentially that program is talking to the TCC saying, move like this, move back, and keep going back and forth, or whatever motions it needs to do. So there is certainly within an observation a set of things that the computer is controlling based on this observing program, on this particular set of instructions that the principal investigator put together with the help of the science staff here at Gemini that help them put their observations together so they can get the data that they need. We don't expect astronomers to be experts in our system. We're here to help them collect the data they need with our equipment.
Thank you for correcting me on that, and for that insight, because I didn't realize that interaction between the program and the instrument happens, but of course that makes sense that it naturally would. Brilliant. So we have about 15 minutes left in our session. I'd first like to bring everyone's attention, Jenny, Zach, Emily, Charlie's attention to the chat. There was a question about books. If there are any good books that we'd recommend for anyone who's a beginner with assuming no science background. And I put some of my favorite ones there. This is for anyone who's interested in space, science, and physics. I put some there, and I would definitely invite you all to add some there too, if you'd like. So from that, I'd like to go to, we have two more questions. Okay, so first, Charlie, I see you. Are you laughing at one of the
No, I'm
books?
not laughing. I mean, in a way, I'm laughing because Brian Cox, I can't not. I would add to that list anything at all by Carl Sagan.
Oh yeah, of course, duh. I don't know why I didn't do that. It didn't come up in my brain. Yeah, the cosmos, of course.
Anything Carl Sagan wrote is, I do like Carl Sagan a lot, but I mean, he had very special insights and an amazing way of communicating. So
That's true.
I look at some of the books that we commonly recommend, like Brian Cox or what's the I'm drawing a total blank. There's a book that what did Hawking write?
A Brief History of Time.
A Brief History of Time.
And a few
It's
books.
one of my favorites. I put it in there
It
already.
is a good book, but also is something that I think if you are a complete novice, I would never throw either Brian Cox or Stephen Hawking at you. I'd be like, no, don't read those yet.
I'll say
That's my opinion.
I mean, I jumped into a brief history of time where I was underlining and defining every word. It took me months to get through this book, but I learned so much because I did,
Absolutely.
but it was challenging. This is true.
It's a lot.
It-
It's a lot.
It's Brief History of Time. It's not a beach read, but it is very, very complex ideas and some of the best ways to be communicating those very, very complex ideas that are really hard. I'll also say I threw one into the chat of Astronomy's Limitless Journey, which is written by an astronomer who's here in Hawaii at the Institute for Astronomy. That's a really great overview of intro to astronomy and also where astronomy is today. I'll also say whatever calls to you at your local library. Just in the science section, you'll be able to find something that'll pick you up. I was the nerd in high school that my senior year I signed up for a community college astronomy class and they got a textbook and I read that textbook front to cover and it is still in my office and it's the still thing that I reference. And so sometimes that textbook becomes really fun, but I feel like that's probably a bit too nerdy to recommend a textbook.
Yes, yes. No, but it's great. A new one that just came out is by Dr. Nia Amara, Painting the Cosmos. And it's about the intersection of astronomy and art and culture. Dr. Amara is a professor of astronomy and astrophysics at University of California, Santa Cruz. And was really excited when this book came out. And it's I think it's very approachable, especially if you have interest in the arts and science. This is a great way to really see not only how they naturally connect and interact, but it's a different way of approaching science too, which isn't necessarily highlighted all the time. So, and beautiful pictures, beautiful images too. So that, and it has some nice cultural background too from various cultures, which makes it even more engaging, I think.
I would also, I'm going to put in the chat here if I can, any books by actually a friend of mine named Sarah Scholes. She is a science writer. She has written a beautiful biography of Jill Tarter, who is one of the pioneers of SETI. She has written a number of books on astronomy and particularly on astronomy. Some I think more broadly on science. I think she's written a book which I haven't read yet. Came out last year. That's looking at more toward nuclear energy generation. But she basically what she's doing is she's looking at science and culture and how we as a culture interact with that science, how we influence it, how it influences us, controversies, things like that. And I think she's a wonderful writer. So I'd certainly, I would call hers beach reads. I would read, I would definitely sit down on a beach with a nice cold beverage and sit down poolside. Yeah. There's a lot of good stuff out there. I think, the thought of just go to the library and pick something out and start reading it, read the first paragraph of the first chapter. And if it grabs you, then go with it. But these are at least a few ideas, I think, to start, if you want that guidance.
Thank you all so much for that. Those are great. I'm just adding here, as Charlie mentioned in the chat, anything by Carl and why I didn't, because that's where I started watching the Cosmos in rerun on PBS with my grandmother. And how could I not have, I don't know why that didn't come to my mind. Charlie, thank you.
One of my favorite things about Carl Sagan is I love his voice and his cadence, the way he talks. And what's great is if you listen to some of his, listen to him speaking, find old recordings or whatever, anything you read that he's written, you will automatically hear in his voice. And it's pervasive and it's a wonderful thing.
It really is. I hear his voice right now. Billions and billions. I'm gonna edit this out of the recording.
Oh, no.
Oh my God, yes. So thank you for the book recommendations, and Jenny and Zach, if you have more you want to add there, please do. Okay, we have about 8 minutes left, so let me get to these last two questions, and then if we have time, I'd love to wrap up with Zach, maybe talking about the special things that you'll be doing on later in the evening after our session. All right, so let's go
Charlie,
back
by
up.
the way, we flipped the Alopeke, if you want to bring that up.
You're on Alopeke now?
Yeah.
Oh, yes. Okay. Well,
Give me a moment
let's-
to, I will pull, I will
Into the
pull that
questions
up.
as we get
Yeah.
that ready. Yep.
yeah, absolutely. I love this. Yeah, Alopeke and Zach. So Zach is our special science guest here, and is doing some unique imaging, unique research here that I would love to share with you all. And we'll answer these questions in the chat as Charlie is bringing up the screen so we can learn more about Zach's research. And Zach, you're now at NASA Ames.
Yes.
Okay.
Yes, I am.
So at NASA Ames, and you're a postdoctoral fellow. For those who are with us who don't know what a postdoctoral fellow is, could you explain that?
Okay, we're centered. Okay.
Yeah, so basically it is a position you get after a postdoc, or after a postdoc. After you graduate with a PhD, it's kind of like, I don't know, it is designed for you to go out into the world and expand your research collaborations. Because for 6 years, basically, you have been researching one project as your PhD, and it's time to go out into the world. But also, I mean, the best analogy I have is it's an internship, effectively, to compare it to other job career paths, where it's normally 2 to 3 years. 2 to 4 years is what I will say now. And so my position is actually a 2-year position plus one if funding is available. So we'll see about that. And so yeah, and then the idea is you build up your research, you get more reference letters, and eventually, hopefully, you get the permanent position. So yeah.
Brilliant. Thank you, Zach. So now, Charlie, this screen, what you're sharing with us looks totally different than anything we've looked at before. What's going on? There's red, there's blue, there's dots squiggling around.
So this is the Alopeke control computer. Alopeke is a visitor instrument, which means it is not an instrument that we maintain. It is an instrument that is maintained by an outside group of researchers. And I'm actually going to throw it back over to Zach because he was very closely involved with Alopeke. And Zach, what can you tell us about what we're looking at?
Yeah, so basically, just a second, I'm trying to figure out what magnitude this target is. That. Okay, so we're gonna do. I just want to get this target started, and then I can come back to this.
Alopeke, Alopeke does have two different cameras called the red and the blue. I'll say that much. And what it does, it's very good at taking lots and lots of images very, very quickly. And that allows certain capability that other instruments don't have, because it can actually look at changes that are happening on very small time scales. And as soon as Zach is ready, he can jump back in and take over for my lame ass explanation.
I was gonna say, how quick is very quick?
He's taking data now.
What are you talking about?
Save Charlie.
Say, Joey.
I mean, so yeah, Alopeke and Zorro is a special instrument that uses a technique called speckle imaging. And so the idea is when you go out and observe the night sky with a telescope, and if you're just taking imaging, you may sit on a target. If you're looking at a really, really faint target, you may sit on it for, a couple of hours. And when you look at the resulting data, you see some stars. They're round, they're circular. There's these nice things that we call PSFs, or points, or they resemble. These stars are in a kind of function that we call a PSF, a point spread function. And so normally the resolution that you get of those stars, what you can resolve down to, is a function of the atmosphere, of what the seeing is, what the atmosphere is doing during your observation. So, for example, right now, the seeing is really good. It's about 0.4 to 0.6 arc seconds, which is really, 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 really small. If you think about it, the moon is about 1/2 degree, and an arc second is 1/3600th of a degree. So that is a really, really small size on the sky. But we can get even better resolution if we go and use some high angular resolution techniques. One of them is adaptive optics, where we basically have the deformable mirror on the telescope. And the whole goal of this is we basically want to take the atmosphere out of everything. Because the atmosphere, as light comes from a star that's super far out, it comes to us, and when it hits the atmosphere, it gets distorted, as it goes through it. And so the methods so if you are able to undistort the atmospheric disturbances, then you can get better. You can resolve closer in objects. And so if, for example, you have two stars that are really, really close to each other, then let's say at 0.3 arc seconds, then if you took just a normal image, you went out with a camera and just stared at the night sky and took a 5-minute image, you would see one single circle. But with these techniques, either adaptive optics, which involves deforming the mirrors of our telescopes, or speckle imaging, which I'll get to, you can then go beyond that seeing resolution and get to what the normal diffraction limit of the telescope is, because we have a big telescope that is a big piece of glass, and just like our eyes can resolve down to a certain limit because of how big they are, telescopes can resolve even closer because of how even larger than our eyes they are. And so by using these techniques, we can beat the atmosphere and resolve closer in objects. And so what speckle imaging does is it takes really, really, really rapid pictures. So right now, these frames that you're seeing on the screen right now are 60 milliseconds. And so if you were to take a 60 milliseconds picture, you get what we call a speckle pattern. And that's what you're seeing right now on the screen are these speckles, which is, the thing in the middle is the star. And if you were to basically take all these frames that we're taking here and added them all together, you would get what you would see if you just took a normal image. But by going at these faster rates, what we're doing is we're kind of freezing the atmosphere in these observations. And then what we do is we go back, we take all this data. So right now we're taking 7 data cubes. And so these 7 data cubes is 7,000 frames. And so what we do is after we take all this data, tomorrow, next week, 2 weeks from now, someone will take this data and reduce it. And basically what they're going to do is run it through a Fourier analysis to examine these frames and see if you can identify whether there are two stars there or whether there's only one. And if there's two stars there, then you've discovered a close binary that would normally not be resolved by a seeing limited image. But if it isn't, then it's just a single star. And so a lot of the studies using this specific instrument are really looking at, the environment around the stars that we're examining. Is there a buddy? There have been other programs that have looked at is a certain faraway galaxy lensed, or does it have a buddy? There are other programs that are looking at whether a star actually has a wind and trying to detect that wind coming off the star. And so the whole point of speckle imaging is to try and get down to the diffraction limit of the telescope by taking these really, really short images, and that's what we're seeing here. And that is my awful explanation of speckle imaging.
His brilliant explanation. So done, and it was so concisely done, and it was done in like 4 minutes. It was brilliant. I know we're a bit over time, Zach, but I want to say thank you first for giving us that explanation and insights, because I think speckle imaging is something new for many people. I know about speckle imaging because it's your favorite thing to talk about. And so when we worked together, you were always talking about speckle imaging and Alopeke, and I'm so grateful to have learned so much, and now we can share it out with everyone here. Now, some people may have heard of lucky imaging. Now, speckle imaging and lucky imaging are similar, but are they the same?
They are different. I'll get to that in a second. Can we go to 14, please?
Yep.
They are different. So, oops, wrong way. There we go. So speckle imaging uses all the data. So we took 7,000 frames in this observation here. Thank you. We took 7,000 frames in this observation, and all of those frames will be used in our data reduction to search for any binary companions. What lucky imaging, okay, that's not what I wanted. What lucky imaging is basically, if you were to take that 7,000 frames and have some metric to determine whether or not which frames are the best frames taken at the best scene. And then you take those 100 best frames and you make a picture out of it. So that is the key difference, I think, between lucky imaging and speckle imaging, is that one of them is really searching for the best frames in a set of really short exposures, and using those as your image, versus speckle imaging, which is more of reducing the data using this Fourier analysis.
Guiding and centered.
And so for your research, Zach, and thank you for distinguishing those two, the speckle imaging versus lucky imaging. And I know we're over time, Charlie, Emily, I'm going to wrap up really quickly here. For your research, can you share any insights on, maybe your targets, what you're hoping to accomplish during this observing run?
Well, my targets have mostly been observed by the Speckle team, so I am pretty well set with these observations. But my research is really on nearby stars, so I'm specifically looking at now stars that could be potentially targeted by the next great observatory, which is called Habitable Worlds Observatory, and really characterizing those stars that will be targeted by the space mission, where we want to try and detect directly image exoplanets around them. And if there's a buddy around them, then that can interfere with the observations to detect those exoplanets. So we really need to characterize whether there's a binary or not. This program, for example, that we're observing for right now is actually looking at our libraries. and determine the binary rate of those. And then there are a bunch of other binary programs as well within the Gemini Q. And we're taking data.
Thank you, Zach. Okay, we have a few questions I want to get back to before we wrap up. So let me scroll back up here. We had a question first about according to Stephen Hawking here, and I mean, I think it's at the bottom here. Yeah, so according to Stephen Hawking, he's predicted that black holes slowly lose mass by giving off heat, or so it's known as Hawking radiation. But if this radiation doesn't seem to contain any information about what actually fell into the black hole, so if this is true, how can information be preserved as quantum theory says it must be? Can we get a quick answer to that?
Sure. The answer is we don't know. So we have not detected Hawking radiation. It should exist. We have a very well developed sense of physics that tells us that Hawking radiation exists. But as you said, Hawking postulated that that should carry no information with it. Quantum mechanics seems to suggest that information has to be conserved. I know that there's a couple of hypotheses suggested, and I'll admit I don't know what they are right now. But I will point out that this is one of those great places where we have these two competing pictures of the world. And clearly, both of these cannot be true as they are. The two of those things, the quantum mechanical picture and the astrophysical picture, are not presenting us a complete view of this action that's happening. So this is kind of the exciting place to study, to try to figure, you've got this thing that's broken, this idea that's incomplete. And so, this goes back to our previous discussions. How do we make these things work together? We formulate some ideas, some hypotheses, and then we try to figure out ways to test them. And to my knowledge, we don't have a working theory, but I think there are some hypotheses that have been presented that, that might explain. And essentially, in either case, what we need is some missing piece. Hawking radiation seems to be a really good description. The conservation of information seems to be a pretty good description. So there must be something else going on that's going to allow both of these things to either going to allow both of these things to take place, or some information that's going to show us that one of these things is incorrect.
Thank you, Charlie.
That is the fastest answer I can give on that.
That's brilliant. That's brilliant. And so if you want to follow up on that, the person who asked that question, thank you. Feel free to email me and I can pass this, pass it around to Charlie and colleagues and certainly get back to you with additional responses if you'd like. Okay, and then next one is, how do you navigate the complexities of interpreting data from distant celestial objects? So how do you navigate that? And then what are challenges you faced? Quickly.
Jeopardy answer.
Oh my goodness. I mean,
And go.
so, I think the best thing I can do is give examples of of why it is so complex. When we collect signal, you see a faint star. Why is it faint? Is the star intrinsically faint? Is it really bright and it's really far away? There's a bunch of different, whenever we collect photons, there is a bunch of different possible factors that can go into making those photons look the way they do, making that light look the way that it does. And so we build a astronomical model, a physical model, not a tangible, solid model, but a model using physics, using our astronomy, that gives us a framework that explains the things that we see that we can test, and then we try to see how, what kind of thing, how we can um, break, we might call break the degeneracy. So how can we tell, is there a way to tell if this star is far away or if it's intrinsically faint? And it turns out, yeah, there are ways we can tell if it's far away or if it's intrinsically faint. And that comes from looking at spectra. So, usually that, we have to find some kind of observation, some kind of tool to use that will help us break through that confusion, because that's absolutely a real problem.
Thank you, Charlie. Thank you so much. And someone did ask for my email, so we may have additional questions coming.
Absolutely.
I'll definitely pass this around. We did just get one more also in the chat. It's just a quick question about whether or not Gemini will have interferometric observations with Gemini South, and if so, what resolutions can we expect, and in which bands? Charlie, I see you're like
So
massaging.
this is such an awesome idea, because of course we do this with the VLBI in radio frequencies all the time. In fact, we have a VLBI antenna here on Maunakea, a little bit below the summit. The problem, optical, we've been doing radio interferometry for years and years and years. And it's hard, but we can do it. And we've gotten pretty good at it. Doing optical interferometry is way harder, and we can do it, but it's much, much harder to do. Part of the reason that we can do radio interferometry is that the wavelengths of the signals are long enough, the frequencies are low enough that if we have a really amazingly good clock at each of the antenna locations, we can sync them up. So we have these very, very highly precise atomic clocks, at each of these VLBI antennas. And when they record their data and they put it on these big data tapes, they're immense, they're huge bricks. They carry a timestamp with them. So when you get all these tapes are all shipped together, shipped to the Array Operations Center in New Mexico, and they take all these tapes from all the 10 different antenna sites, and they basically load them in the computer, and they have all the timestamps, and they can match it up, and presto, they can analyze that. And it works with these best clocks that you can possibly get. The problem is, when you're looking at optical frequencies, the frequencies are much higher, the wavelength's much shorter. So essentially the data cycles are very, very, very short, very, very fast. Many orders of magnitude greater than radio signals. So you would need a clock that's that much more precise if you're going to do it separated by a large distance. If you're going to do interferometry right now, optical interferometry, we're limited to places where you can actually take the light from each telescope and physically combine that light, let that light interfere. And in fact, there are radio observatories where that's done. But the only way you could do it, that's obviously impractical for Gemini North and Gemini South on two different continents, thousands of miles apart. You can't send the light directly to each other. So it would have to be recorded with a very sensitive timestamp, and we do not have that technology. That is physically out of our capability right now. So it's an awesome idea. I would love to see that. That would be some crazy, amazing resolution. But the flip side of that is we still have to combat the optical distortion by the atmosphere at both locations, and that's going to be greater than any possible gain we could get. So I think most of the places that have tried to do optical interferometry, even the physical combine the light way, a lot of them have given up on the idea because it's really hard and the gain is not huge because you're still fighting with atmosphere.
Chara wins.
Say again?
Chara's doing it.
I say nobody's doing it, but I mean, it is, I cannot be overstated how difficult that is. In the radio, piece of cake. We have beautiful radio arrays in New Mexico, in Chile, scattered from one end of the United States out to the other.
I think the question specifically refers to Gemini North and
And
Gemini
Gemini
South doing
South.
it. I think it's a long shot.
All
Long
right.
means we need distinct technological advancements that we just do not have right now. But it would be cool.
I will hope that in the future we can overcome some of these challenges and see, see what we can make happen.
And if I can add one last thing, there are a lot of gains that we can get from these two telescopes separated by this great distance that are not interferometry. And, part of that is they cover, they have an overlapping part of the sky, but they also cover parts of the sky that the other can't see. But the other thing is, because they are in two different locations, if there are things that they can both observe in that overlapping part, that does allow some very high precision parallax measurement. So we can, making a measurement of a nearby object in particular from two different locations on the Earth's surface gives you ways to, say, figure out distance. And if you figure out distance, then you know brightness, and it goes on and on from there. So there are things that we can do using both of the telescopes to look at the same thing. Interferometry is not one that's going to be. I feel safe to say Gemini will never be able to do that because the lifetime of the telescope is shorter than any conceivable path to that high precision of timestamp.
They have at the summit a hole that is dug part way from Subaru to Keck.
Yep.
Because they wanted to make an interferometer not only between the two Kecks, but also involving Subaru. And then they never pursued that.
Yep.
Yeah.
That's right.
But that's physically combining the light, and you can do that over a reasonably short distance, but not much longer than that.
But it costs a whole bunch, and there's all these problems that you have to fix, and you have to have all these experts on hand, and it's just too much money. The problem is, it's like all the problems of one telescope, all the problems of the second telescope, all the problems of the third, if you've got a third, and then take all those problems and then square that. Yeah. You're not just adding those together, you are, because of communication issues. I've worked with radio astronomy, and it's brilliant, and it's difficult, but it's something we've gotten very good at doing. But the difference in scale, just because of the difference in frequency, that difference in wavelength is staggering. And the weather and the personality challenges.
That's another issue entirely.
That's
Yeah, but
another
it is
issue entirely. So someone had asked somebody had asked about somebody had asked something about the intersection between psychology and astronomy. Observatory operations.
Yeah.
Observatory operations and leadership would be a.
I did want to highlight on that. I sent some recommendations, and I wrote out a response of yes, there is room. Oftentimes, especially in HR, of course, education. But some papers that I was also recommending of, if you're really getting into research, I can never promise you a job. I can't promise funding. I'm still working that out. But the one interesting area of research that sparked my interest was the High Seas project, which was studying here in Hawaii there was people who were living in a simulation Mars habitat, and the entire study was about their psychology of isolation, in equivalent of living in very, very isolated environments as well. And I think there's an entire area of research that would be interesting from a psychology perspective for that. If you're looking into research, I could also see we had such a deep discussion here about astronomy and science and how that fits within our mindsets and our daily lives. And there could be a whole interesting psychological study on that and how science education and astronomy education alters people's brains. I think there's a lot of great intersection there too.
You're talking about the one that was up on Mauna Loa, right?
Yeah, the High Seas Project. Yeah.
Yeah, I had to deliver goods to them once a week and water. And we had to sneak up and like not let them know we were there, even though it was paper thin walls. They knew we were there and they were all trapped together. So anything new and exciting, I'm sure, and we just kept expecting to hear like arguments and fights going on from the outside, because if you're trapped with somebody that long, like how difficult would that be? And the cases that we had to deliver were labeled Menahune, um, because they
Oh,
would magically appear for them, and we couldn't be in sight when they claimed them. It was really interesting.
Nice.
wow, that is really awesome, Jenny. I didn't know you did that. That's cool. What a dynamic session this has been. And I know we're almost 30 minutes over. This was we had so much engagement. Zach, Jenny, Emily, Charlie, thank you so much for allowing us to shadow you, Zach and Jenny, for allowing us to shadow you, and Emily and Charlie. Thank you for being amazing science hosts here for this session. And I'd like to congratulate you, Charlie, on a brilliant first session for you. Thank you so very, very much.
Yeah, good
This was
job, Charlie.
amazing. Yay, Charlie. Zach, I wish you success in the rest of your observing for this run. Jenny, thank you again for all that you've contributed. Emily, you're amazing as always. Thank you so much for helping with the chat, answering questions, putting things in the chat, also answering questions there. And then Charlie for bringing us all together, keeping us informed on what's going on, showing us the amazing science, and giving us the insights to really appreciate what we were seeing. Thank you.
Dad, it looks cool.
Wow. It looks cool. It's speckle data. You've seen
Yeah,
one speckle,
right?
if you've seen one speckle, you've seen, what is it, 10 million speckles?
Oh,
Five.
Did you see the binary?
see, I knew Zach was gonna have something to say.
Did you? I
Yeah.
mean, we observed a calibrator that was a clear binary.
Binary, and there was
I
cool.
saw that.
Watching that, I was going to interrupt, and I was like, "Oh, if that's still up at the end, we should throw to that."
Oh my gosh. Yes. No, we're gonna go
Okay,
ahead
we're
and
going in
wrap it up
seconds.
here. You all, thank you
100
so
hertz.
much. Those of you in the audience who joined us, great questions. Thank you for your questions. Thank you for your comments. Thank you for sharing with us where you were joining us from. It was great to have you, and we look forward to seeing you in a future Shadow the Scientist sessions. Take care, and we'll see you next time. Aloha.
Aloha.
Aloha.